Hey guys, this is Carrie, and in this video we're going to be taking a look at lesson 6. So let's get started. Let theta equal 120 degrees. Which of the following is true? So the most important thing here is when we're trying to figure out the sign of a trig function, we know that for our quadrants, theta is going to be, for our graph of the angle, theta is going to start in the same place that it always starts, on the positive x-axis. And then we're going to rotate 90 degrees would be here. Another 90 degrees would be 180. 180 plus 90 would be 270. And then if we went all the way around, that would be a full circle. So in our case, theta is 120 degrees. So we're going to go somewhere in between 180 and 90. So it looks like it's going to be around here. Now we also know from our mnemonic to help us remember the signs of the trig functions that all of the trig functions are positive here because all students take calculus. So our terminal side is in the S quadrant, which means that only sine is positive. And so it's the first one. So cosine and tangent would be negative numbers because they're not positive in the S quadrant, only S sine is. Carrie believes that the tangent of 240 degrees is negative square root of 3. Without even looking at any of the numbers in the problem, explain how you can tell that his answer is incorrect. Well, if you graph a 240 degree angle, let's just label our key values first. Well, this would be 0, but also 360. If we graph a 240 degree angle, that's going to start on the positive x-axis. We're going to rotate past 90, past 180, all the way into the third quadrant. And for a 240 degree angle, that falls in our all students take calculus T quadrant. This T means that tangent of theta is a positive number in this quadrant. But what did Carrie say? That it was negative? That can't be. So we know that in quadrant 3, tangent of theta is positive, not negative. So we can always check the signs positive or negative of our answers using this mnemonic. Now we've got one of these sort of tough questions where they give us sine of theta and they ask us about cosine of theta. So let's take a look at this one. If sine of theta is negative 15 over 17, okay, so let's graph it. And theta is an angle in the fourth quadrant, okay, so we're going to be in the fourth quadrant. So here's theta. And let's see, what is the value of cosine theta? So when we're looking for the value of cosine theta here, we have to remember, originally when we learned about sine, cosine, and tangent, we learned the mnemonic so, ka, toa. Now this mnemonic was really helpful when we had theta as an acute angle in a right triangle. But when we moved on from theta being the acute angle in a right triangle, we saw that we had to update these definitions to the coordinate plane definitions. So sine was actually equal to the y-coordinate divided by the radius. Sorry, I'm going to rewrite that R. Cosine actually, so like where this came from, right, was the y-coordinate divided by the radius. That was the same thing as opposite over hypotenuse. Cosine was adjacent over hypotenuse. In coordinates, that would be the x-coordinate divided by the radius. And tangent of theta would be the opposite divided by adjacent, so that would have been y divided by x. So our old definitions, SOHCAHTOA, lead to these new definitions right here. So we know that if we graph this, we have a point, and we have an x and a y coordinate for that point. We also have an r value, which is the distance, the radius out to that point. So let's fill in these blanks now. Sine is y over r. So if we go into the given formula, we know that these are our y and r values. R is a distance, so it's always positive, meaning that this negative sign in the problem must have gone with the negative 15, so the y-coordinate must be negative. And if we look at our graph, that makes sense because our y-coordinate is going down 15. Now, cosine is supposed to be x over r. Now we have a bit of a problem here. We're missing our x-coordinate. So in order to find our x-coordinate, we need to use the Pythagorean theorem because this actually has a mini right triangle in it. So if we plug in a squared plus b squared equals c squared, substituting in gives us x squared plus, this is really, even though it's down 15, when we think about it geometrically as a triangle, the length of that side is still 15, and 17 is the hypotenuse, 17 squared. So we get x squared plus 225 equals 289. And I keep using the same examples because they give us nice answers. X squared is equal to 64. We take the square root of both sides and we get that x is equal to 8. Now, that side length is 8, but when we plug it in as a coordinate, we have to think, well, should it be positive or negative 8? Well, because we moved to the right on the x-axis, positive 8 was the correct choice. So it looks like our cosine will be 8 for x, 17 for r. So cosine of theta is 8 over 17. Now to verify this answer, let's look at our quadrants one last time. All students take calculus. Since we're in the fourth quadrant, cosine should be positive, and we find that cosine is positive. So we know that we're good to go. Continuing on, we're going to take another look at this derivation from last class, because I think this was a complicated derivation and something important to see. So one of the questions that we've had throughout this is, sometimes we're able to do these sine, cosine, and tangent problems without a calculator. Other times we have to rely on a calculator. And so there was this really helpful idea we looked at last class called a reference angle. So let's rederive where that comes from. So in the following problem, you're given an angle theta. In the other two diagrams, you're given the same terminal side. Yep, that does look like the same terminal side. In the second diagram, to draw angle alpha, draw an acute angle between the terminal side shown and the closer part of the x-axis. So terminal side, closer part of the x-axis. We've got two choices. We have either this green side or this pink side. Now I think the green side is the closer side, so let's put our angle alpha here. In the third diagram, to draw angle B, draw an acute angle between the terminal side and the closer part of the y-axis. So we have this pink side here, or this orange side here. Now the closer part of the y-axis I think would be right here, so let's make this beta. Okay, so now let's find the sine, cosine, and tangent of these things. So for this one, theta, we can just use our new formulas because theta is graphed in standard position, which means that those new formulas, the ones we just used in the last problem, definitely work. So we're going to do y over r, cosine is x over r, tangent is y over x. And again, skipping finding the radius, you would just use the Pythagorean theorem. The radius for all of these is going to be 5. You can just do a squared plus b squared equals c squared if you don't trust that 5. So sine here is going to be y over r. Cosine here is going to be x over r. Tangent here is going to be y over x. Now we usually rewrite this. A positive divided by a negative will make the whole thing a negative number. So we usually don't leave negatives on the bottom of fractions. All right, continuing on. For these ones here, we have a bit of a problem, which is they're not graphed in standard position. Alpha is this tiny angle here, not the same angle that theta was. But because alpha is a tiny acute angle, we can imagine it inside of a right triangle. And when it's inside of a right triangle, we can see it from a geometric perspective that if this were going back 3, this would have side length 3, and this would have height 4. And so because this isn't graphed in standard position, we can't use these coordinate plane definitions that we become so reliant on. We actually have to go back to so, ka, toa. And so going back to these, because we're in a triangle, leads us to sine would be opposite divided by hypotenuse. Cosine would be adjacent divided by hypotenuse. And tangent would be opposite over adjacent. Now similarly for this next one, Let me not use orange because we used that already with the... let's use this brown color that I've never used. All right, so similarly for this one, we have to not use our coordinate plane formulas because beta is not graphed in standard position. Standard position means we start on the positive x-axis. We do not start there. So we have to try to draw a triangle that involves beta. And we're able to do that, luckily. So here's our triangle with beta in it. Beta is this tiny acute angle right here. The hypotenuse is 5. Because we go back 3, the side length here is 3. And because we go up 4, the side length here is 4. So sine of beta, we can't use these. We've got to go back to our original SOHCAHTOA formulas because it's not graphed in standard position. So we have opposite for beta over hypotenuse would be 3 over 5. Adjacent over hypotenuse is 4 over 5. Tangent is opposite over adjacent, opposite over adjacent, 3 over 4. Now, if we compare our answers, we make a big realization that we made in the last class, but it's worth seeing one more time. Our big realization is looking at theta and alpha, these answers are incredibly similar. So the sine of theta is almost equal to the sine of alpha. And that's not the case for beta. Here it's 3 over 5, and in both of these we had 4 over 5. So sine of beta is not as useful, or not as related to these two. Cosine of theta is very similar to cosine of alpha. They're almost the same thing. But cosine of beta is 4 over 5, which is not the same thing as 3 over 5. And tangent of theta is very similar to tangent of alpha. They're the same exact thing except for the sign. But tangent of beta, totally different. 3 over 4, these are 4 over 3, and 4 over 3. So basically, theta and alpha give the same numerical answers. 4 over 5, 4 over 5, 3 over 5, 3 over 5. But the one thing to keep in mind is that sometimes the sign is different. Sometimes theta is negative when alpha is always positive. And so that leads us to a really important idea. We started to call alpha the reference angle. And the reason why is it provides a reference. It's easier to work with sometimes than theta. But because they give such similar answers for each of the trig functions, it's a very useful angle to keep in mind. Alpha is called the reference angle. And it's important, when you want to construct alpha, alpha is always going to be an acute angle between the terminal side of theta and the closer part of the x-axis. So let's see how we can use alpha in a couple of examples. So I know these are the same examples as last time, but I think this is complicated enough that it merits to see. If we wanted to find the sine of 330 without our calculator, we'd have to imagine the coordinate plane. So the sine of 330 degrees seems like an impossible problem to find. However, we know that the sine of theta, let me write that out, sorry. The sine of theta is going to be almost the same thing as the sine of alpha. And so if we wanted to find the sine of theta, we could look and find alpha instead. Well, alpha is always going to be the positive acute angle between the terminal side and the closer part of the x-axis. So between the terminal side, the closer part of the x-axis, this acute angle. If we had 330 here, if we had alpha, the whole thing would give us 360. And so this little missing piece here has to be 30 degrees. So that is alpha. Well, that gives us a huge benefit to finding sine of theta. We know now that the sine of theta is going to be very similar to the sine of 30 degrees because 30 degrees is alpha. And the sine of 30 degrees, that should ring a bell. When you're thinking in your head the sine of 30 degrees, we have our 30, 60, 90 reference triangle, which if you have it memorized, hopefully you do. It's a little harder because you don't talk about it each day when you're at home, But if we talked about it each day in class, I think you'd have it memorized. 30, 60, 90 triangle, so 1, 2, square root of 3. And so sine of 30 degrees is, or sine of theta is, now we're going to write exactly equal to the sine of 30 degrees 1 over 2. But if I want this to be exactly equal to, I'm no longer writing those curvy equal signs. The thing we have to keep in mind is that the signs, positive or negative, can sometimes be different. So we do a check. All students take calculus. Only cosine should be positive in this quadrant, which means that sine should be a negative number. And so our final answer here is sine of theta equals negative 1/2. Determine the cosine of 225 degrees without using your calculator. All right, so we graph this one. Same procedure as last time. Cosine of 225 is in the third quadrant. Now we need to find the cosine of theta. But we know that theta is 225 degrees. We know that that's going to be really similar to the cosine of the reference angle. To find our reference angle, we draw, let's see, alpha is always with the x-axis. So terminal side, closer part of the x-axis, here's alpha this time. And this alpha is a little harder to find. It's nothing to do with 360 like we said last time. In fact, we want to see this 225 as having, well, this top part was 180. So then alpha would be the leftover piece, the piece that goes past 180. So in order to calculate that, we could do 225 degrees, subtract off this top 180 degrees, and that will leave us with 45 degrees for alpha. So the cosine of 225 degrees is going to be almost the exact same thing as the cosine of 45. And hopefully when you hear cosine of 45, that makes you think, oh my gosh, the 45, 90 reference triangle. So this one was 45, 90, 1, 1, because the angles are congruent, the sides are congruent, and then square root of 2. So cosine of 225 degrees is going to be exactly equal to, cosine is adjacent over hypotenuse, 1 over the square root of 2. And then the last thing here is the sign. Is it positive or negative? So if we go through and we do an all students take calculus, we end in the third quadrant, our terminal side. Tangent should be positive only, which means cosine is negative. So we had our final answer for the cosine of 225 degrees. All right, now I switched these up from last time, so please take a look at these and do your best to figure them out. Once you're done with that, we're going to continue on to reciprocal trig functions. All right, so we've done a lot with trig. And next class, we're actually going to have a quiz. We're going to do it on Delta Math, but you'll get the directions for that next class. So kind of going through that whole path that we used to get from the very beginning up to this very sophisticated point where we're using reference angles is a lot to take a hold of. The quiz is going to be open book, which means you can refer back to any of these videos, you can refer back to any of the lessons, and you can refer back to your notes. But it is going to be helpful for us to review those key ideas. So the way that we're going to review those key ideas is in the context of something new. So there are actually not just 3 trig functions, sine, cosine, and tangent. There are actually 3 more. And each of those new ones, for a total of 6, is very related to one of these. In fact, they're called the reciprocal trig functions, and we're going to learn about them right now. So before we get to the reciprocal trig functions, the reciprocal of a fraction is the fraction you get when you flip the numerator and denominator. For example, the reciprocal of 3/2 would be 2/3. What is the reciprocal of 4/7? Well, all you do for a reciprocal is you flip it, so 7 over 4. They're not the same thing, but they're definitely related. So it turns out that very frequently you end up having to flip your trig functions, so we actually give those different names. So here's the answer. There are 3 functions called the reciprocal trig functions, and these are all going to be flips of the normal ones, which are the reciprocals of the 3 normal trig functions. Fill in the blanks at the end of the second and third bullet points. The reciprocal of sine of theta equals opposite over hypotenuse is called cosecant. Whoa, okay, cosecant. And usually you put that as CSC theta, but we read it cosecant. And is given by the reciprocal of the original fraction. So the opposite, the flip of sine of theta would be cosecant. So opposite over hypotenuse becomes hypotenuse over opposite. See if you can read through the next two to find out the definition of secant and cotangent. Okay, well hopefully you saw for secant, it's just going to be the flip of cosine. So this one, secant of theta, is going to be hypotenuse over adjacent. You just flip it. Tangent of theta, the opposite of that's called, or the reciprocal of that is called cotangent of theta. So for cotangent, you do the flip, it's going to be adjacent divided by hypotenuse. Now all of this is kind of bunched together and hard to read. So let's isolate some key facts. Cosecant theta is the flip of sine of theta. Secant theta, flip cosine theta. So this one is going to be secant theta is a hypotenuse, got to flip it over adjacent. And then cotangent is the flip of tangent theta. And so if we flip tangent theta is usually opposite over adjacent. We'll flip it so we get cotangent of theta is adjacent divided by opposite. And it's not worth memorizing these, I don't think, in terms of like hypotenuse and opposite. If you just remember the thing that they flip, then it's easier to remember, I think. So cotangent is pretty easy to remember. You know that it's going to flip tangent, so you just remember tangent and you flip it. These ones are a little bit weirder, but you can remember that cosecant, the C flips with the S, and here the S flips with the C. So cosine and cosecant don't go together. That might be too much though at this stage, so let's continue to talk about this and get some practice with it. Use the diagram below of triangle ABC to answer each of the following questions. Explain why cosecant of A is 25 over 7. Well, if A is our focus angle, the way that I like to think about all these reciprocal trig functions is pretend they're normal trig function problems. So sine is so, ka, toa. We know that cosecant is going to be the opposite of sine. So cosecant is going to be hypotenuse over opposite. And labeling our triangle, we have hypotenuse, everyone's mixed it up. Hypotenuse over opposite. Yeah, that's correct. All right, so for checkpoint 4 here, take a minute and see if you can figure out secant A and cotangent A. All right, well, we know secant A is going to be the opposite, or the flip of cosine. So we do hypotenuse over adjacent. So you should have gotten 25 over 24 here. And we know that cotangent is going to be, let's use cotangent in green. Cotangent is going to be the flip of tangent. And so if tangent was soka toa, then opposite over adjacent would flip to adjacent over opposite. And that would give us adjacent over opposite, 24 over 7. Okay, so we can actually continue to build on these ideas. It turns out that the same reference triangles that we used before are really useful for this as well. So let's look at an example of that. So let's draw our 30, 60, 90, and 45, 45, 90 triangles. Now I see a lot of students do what I just did, which is draw the triangles with the angles, but they're totally worthless unless you put the sides as well. So make sure you put your 1, 2, square root of 3, and 1, 1, square root of 2. Alright, now that we've got our sides, cosecant 30 Oh man, this is one of the new ones. So for cosecant, that's the opposite of sine, so we flip sine of 30. So sine of 30, this is another way you can do these. Sine of 30 degrees is equal to 1 over 2. We know that we're supposed to flip sine of 30. So whether you flip it right away and you get 2 over 1, or whether you find sine first and then flip it, it would give you 2 over 1, which is just 2. So cosecant of 30 is 2. Now another way you could have done that was, right, you could have said, well, sine is opposite over hypotenuse, so cosecant of 30 is going to be hypotenuse over opposite. And when you do that, you still get the 2 over 1 that we got. Let's skip this one and you can do that. For secant of 45, secant is the flip, and you can keep looking these up back here. Secant is the flip of cosine. So cosine is usually, cosine is usually adjacent over hypotenuse. So secant of 45 degrees is going to be hypotenuse divided by adjacent, the flip of that. So secant of 45 degrees is equal to hypotenuse divided by adjacent, square root of 2 over 1, which is just square root of 2. A circle centered at the origin has a radius of 5 units. The terminal side of an angle theta intercepts the circle in quadrant 2 at point P. The y-coordinate of point P is 4. Draw a diagram of the situation described. Okay, this is quite a bit. Quadrant 2, point P. So that's going to have an x and a y coordinate because it's a coordinate in the coordinate plane. So here's theta. The terminal side of the y-coordinate of point P is 4, so they're giving us the y-coordinate is 4. They also gave us that the radius is 5. All right, so finding the x-coordinate here, we've got to think about this as a triangle. So this is 4, this is the x-coordinate. So we're going to have to do an a squared plus b squared equals c squared. We plug in x for a, 4 for b, 5 for C. So x must be 3. But pause for a second, because we went back 3, so it should be negative 3. All right, cool. So now it turns out that just from this diagram, you're able to find all of the following things. So sine of theta, well, that's usually y over r. And we're going to the coordinate plane definition here because this angle is not, theta is not actually part of that triangle. It's too big to fit in a triangle, so we need the coordinate plane versions. Cosine is x over r, tangent is y over x from our coordinate plane formulas. These are just going to be the flips, the same way that we had before. This one is going to be r over y. We're just flipping this one. Secant theta is going to be the flip of cosine, so r over x. Cotangent is going to be a flip of tangent, so x over y. All right, let's write them all down. Y over r, 4 over 5. X over r, negative 3 over 5. Tangent of theta, y over x, so 4 over negative 3, which usually we would write a positive divided by a negative. We'll make the whole thing negative. Now these are all just going to be the flips. So here we go. If we flip, so r over y, that's 5 over 4. This one is going to be r over x, so 5 over negative 3. Or you'd probably write that as negative 5 over 3, because we don't like to have a negative on the bottom of our fraction. And then here, this would be the flip x over y, negative 3. I'm just using the flip, negative 3 over 4. All right, so hopefully in this lesson you learned about cosecant, and I always like to say them in this order because I like to say sine, cosine, tangent. If you remember cosecant, secant, cotangent, it's in the same opposite order with the ones that pair up. All right, guys, so hopefully you found this video helpful. We'll have a quiz next class. So talk to you guys soon. Bye.